Advanced haptic systems, creating a more immersive digital experience. Dear colleagues, today I present a study focused on the development of advanced haptic systems and their role in creating a more immersive digital experience. At a time when visual and auditory interfaces have reached a high level of sophistication, a fundamental question emerges: can digital interaction be considered complete if the sense of touch is absent? The central thesis of this research is that haptics, as a technology enabling the transmission of tactile and kinesthetic information, represents the next step in the evolution of human-computer interaction. While screens and speakers have become standard communication channels, touch remains the most immediate and intuitive mode of engagement with the environment. For this reason, the integration of haptic systems into digital platforms significantly transforms how users perceive and experience virtual spaces. Within the theoretical framework of this study, particular attention is given to the neurophysiological foundations of tactile perception. Mechanoreceptors in the skin detect pressure, vibration, and temperature, and this information is transmitted via the peripheral nervous system to the somatosensory cortex. This biological mechanism serves as a model for the design of haptic interfaces. In other words, to create convincing digital sensations, it is essential to understand how the human organism naturally processes tactile information. The paper further systematizes existing categories of haptic technologies, including vibrotactile systems, force feedback mechanisms, and advanced exoskeletal devices. Vibrotactile systems, most commonly implemented in mobile devices and controllers, provide basic feedback through vibration. Force feedback technologies, widely applied in simulations and medical training systems, generate resistance and deliver a realistic sense of interaction with virtual or remote objects. The most advanced systems integrate multiple modalities, enabling precise control of force, texture, and motion. Special attention is devoted to the application of haptic systems in virtual and augmented reality environments. Empirical findings indicate that the integration of touch significantly enhances the sense of presence, that is, the subjective experience of being in a virtual space. In education and medical training, haptic simulations allow for the safe practice of complex procedures. In rehabilitation contexts, tactile feedback contributes to improved motor recovery. In industrial applications, remote robotic control becomes more precise and intuitive through the inclusion of haptic feedback. Methodologically, the study relies on experimental research designs that assess user experience, task performance accuracy, and cognitive workload. The results demonstrate statistically significant improvements in performance in environments where haptic feedback is integrated, compared to systems based solely on visual information. Increased user engagement and reduced error rates in complex tasks were also observed. Nevertheless, the development of advanced haptic systems is accompanied by several challenges. Technical limitations include device miniaturization, energy efficiency, and the precision of sensory reproduction. At the same time, ethical considerations arise regarding prolonged exposure to simulated tactile stimuli and the protection of data related to users' biomechanical characteristics. In conclusion, advanced haptic systems should not be viewed merely as an extension of existing interfaces, but as a paradigm shift in digital interaction. By introducing the sense of touch into digital environments, technology becomes more natural, intuitive, and aligned with human experience. The future of human-computer interaction will depend not only on what we see and hear, but also on what we are able to feel.